Okay, so I think it's about time for this online lecture. So very nice to have all of you in this online Zoom lecture about introductory of the operations research. First, let me know if you could see my screen. And what we are going to discuss today is about overview and discussing how the operations research, what operations research it is, and how we could utilize our operations research in our daily lives and makes the science of makes a better society, and it is also the science of better. Okay. So if you have any questions and comments, I guess you may able to like use the tool. I guess it's a raise hand in the Zoom lecture, or you just directly share your comments in the chat box. Okay, let's move on. So okay, let's move on. So we might starting with a very interesting question about how we could looking for the common sense or the common property for some of the tasks that you might realize in daily lives. For example, like what about the subway scheduling and when you do the ride hailing apps and try to like get some food or get some packages. And what about like in healthcare, how you scheduling the nurse and the doctors to each of the departments? And more fancy cases is okay when you do the when you try some AI related apps or do some tasks, you might one interesting question is about okay, what they all have in common. So if you check their fundamental core parts and how they exactly implemented, you might realize that okay, all of them they have heavily relied on the advanced mathematics to operate these type of the tasks. Okay, so this is what I highlighted in blue of the third bullet point. So the right-hand side, just two examples. One is the subway scheduling of Singapore, because I am a faculty member in the National University of Singapore, so I somehow more familiar with what it looks like. And the second is a type of the screenshot of one ride-hailing apps commonly used in Singaporean, but also you could just think what you used in your cell phone, like the Uber, like the Lyft, like the Didi, etc., etc. Okay, let's move on. So see, in previous slides, we somehow realized that, okay, there are a lot of daily tasks or some fancy applications about artificial intelligence. They have common sense, need to like making decisions, they need to like do the mathematical modelings in order to get some good strategies. And in a more formal definition, this is kind of the origin of the operations research. And as we showed in the left side of this column, the operations research, you could just consider it's like a scientific or mathematical process that trying to, okay, collecting the data, collecting the information from your daily lives and translate it into some kind of the insights. These insights may be just from your heuristic, just from your daily experiments, or if you want to do it in a precise way, in a mathematical way, you could use the tools that we were going to introduce in the next few slides that translate this kind of insights to make better decisions. Okay. And in order to deal with this type of the development and applications of analytical methods to improve the decision making. So if you check the right-hand side figure we showed here, this gives a very, very high-level hand-waving way to how you get starting from the purpose of the problem, collecting data, making a good mathematical analysis, or just making the heuristic analysis from daily experiments, and then do it in a good propose a good decision, and then try to implement it. So this is a very brief way from the data to decisions. And for a very brief definition for the operations research, it includes all these 5 parts. But if you want to do it, or if you want to consider it in a very, very restricted way, or you want to ask, okay, this seems like very vague, and like the data mining, data analytics, some also role that played like the machine learning, they also did something similar. But what's the most difference of that differentiate the operations research from other part of the field of study is the analyze. So it's kind of helping you a good framework of how you getting the data, turn them into a mathematical model, and then find the absolute best way, other than we just rely on our daily experiments to make a decision. And also, such decisions are somehow legal or feasible in some sense, because we should notice that in our daily lives, or in the tasks that you are going to meet in your future career or industry, we cannot do with unlimited resources, or with unlimited time, with unlimited of the energetic. So we could do something, we could find out a best way within some control, or under some limited resources. That's what I mean. Okay. Any questions and comments? If you have, you could just share your questions and ideas on in the chat box, and I will check it. No? Okay, so far so good for now. So let's just quickly get into the most exciting part that I would like to share with you in this online Zoom lecture. So every time I'm instructing the OR courses, some of the students would like to ask that, okay, you are talking about operations research. It seems like relatively industry courses, but then after like 1 or 2 courses, you just directly go into or focus on a topic that's called the linear programming. That seems okay, a little bit different from what we have expected. So the linear programming, this name seems very mathematical. And I would like to wondering, okay, why we should learn this, and why this takes about, let's say, 80% or 70% of this introductory level OR courses. Okay, so to answer this question, I could list many reasons, but I guess the most simple and direct reason is that the linear programming is the most fundamental and widely utilized and good mathematical tool to do the operations research analyze. That as what we showed in previous slide, this part. And then also, you could see that I list 3 bullet points about why the linear programming is important. It's utilized for a lot of big companies. It's the backbone of the AI infrastructure. For example, if you want to like managing managing cloud center or data center, that you need to first scheduling your electric power and looking for a good location, because the physical, even though that the physical location could just speed up your communications, your communication with the center survey, for example, like faster in nanominutes, not nanominutes, nanoseconds every time. But you have to like communication with the center server, millions or billions in every second, and the cumulative speed up will be very, very great. And also, if you check some big tech companies, you might realize that companies like Amazon, Microsoft Research, Google, and also some companies like the ByteDance and also the Huawei, they all have integration, the optimization techniques, all are tools, especially the linear programming in their decision makings. But they do it in a way that in their back end. They didn't show it in the app. Okay. So seems like the linear programming is very important. Is sharpen weapon for the operations research analytics. Then we might asking, okay, if we want to learn a linear programming, what type of the components the linear programming it has. So the linear programming components has 3 major parts. The first part is about its decision variables. So usually it's corresponding to what we are going to decide, like some of the alphabet variables like the little x, little y that we have used a lot in our high school study of mathematics. And we use this kind of the decision variables to denote, for example, how many units we would like to produce. Second is about the objective function. So the objective function, as the name shows, it's like of the ultimate target that you would like to achieve. And usually in as an industry problem or something that you would like to choose the best strategy, best way, you always want to, for example, maximizing your profit or minimizing the cost or minimizing the payment that you would like to. And then lastly is the constraint. Because we noticed that to make a decision in our daily life and in industry, the resources are limited. And usually the resources corresponding to the time that you could devote it to, the energetic that you could put, the money and the payment that you are willing to use, and also some kind of the label that you would like to devote it. Okay, so we have always meet a lot of limitations, but what we could do for this linear programming to help you have a good OR analytics, make the decision, is we should do our best within this kind of the restrictions. Okay. So let's check an interesting linear programming example where I always use it in as the first example in our operations research course. And the setting is very simple. Assume that you are a boss of a furniture manufacturer, and this factory produces two items. One is a table and another is type of chair. So the table and the chair, you just consider them as some kind of the uh, realization of two abstract items. And for these two items, since you are the boss, you always want to maximizing your profit. But and you know that the profits that you could get for a unit of the first item, which is a table, is $30, and the unit profit that you could get from the second item, in our cases, is chair, is about $20. Okay, but as we discussed before, we always have limitations on what we could use, what we could devote it to. So the production is constrained by the availability of 10 broad feet of the first resources, which is wood, because we would like to somehow produce the tables and the chairs. But you can consider it as some abstract resources. And the 8 hours of labor is the second type of the resources limitation that we placed on this problem. Okay. And for each of the first item, the table requires the 2 unit of the wood and 1 unit of the labor, or 1 unit of the second resources. And similarly, the chair requires 1 broad feet of the wood and 2 hours of labor. Okay, so the setting is very straightforward, and I would like to show you how the linear programming looks like. As we could see in the right-hand side column, since we would like to maximizing the profit, so we return out the maximize in the top left part to emphasize or to highlight that, okay, this is a maximization problem. The best way or the best strategy that we could do, we would like to attempt is to maximizing the profit value. And maximizing what? We will need to maximizing our objective function. And here the objective function, it contains 2 parts, where the first part is 30 times x1, because we notice that every time if we successfully bought one buy one table or sell one table, we get $30 profit. And similarly, the second component is the 20 times the x2, where the x2 denotes the number of chairs that we got. Okay. And the total profit is nothing but we summation them together. And this capital Z just denotes, okay, the value of our current profit if we consider different type of the choices of number of tables and the number of chairs. And after that, you might see this little s dot t dot. This is just a shorthand of subject to. So it refers to that, okay, I would like to maximizing this objective function subject to under the control of the resources that we write on this part. As we could see that we have 2 uh, linear inequality equations, which represents for the constraint on the wood and the constraint on the labor hour. And also we have two sign constraint with respect to the decision variable x1 and x2 to make them okay. They should be greater than equal to 1 because we might not or would like to consider the case that okay we sell a -1 table, something like that. Okay. And one interesting thing that I would like to point out is that this S point T2 point, we always refer it as subject to, and this is not such that okay. So the subject to means okay, the objective and the decision variable should under the control of the constraint that we listed here. Okay. And if you have good attention, then you might see that in the right-hand side figure, we could somehow get a geometric illustration. The horizontal line denotes the number of tables that we would like to output. And the vertical line denotes the number of chairs that we would like to output. Okay, and since we know that the x1 and x2, they should be greater than equals to 0. So for this figure, as a good geometric illustration, with all the x1 and the x2 value, we all starting from 0. Okay. And the first wood constraint, 2 times x1 plus x2 less than equals to 10. Okay, this corresponding to this red line, but you should be a little bit careful is not red, this green line. This green line only if you are directly at this green line, it only gives you the case that 2 times x1 plus x2 equals to 5. You can check that if x1 equals to 4, and you move on a little bit and to the green line, you see that the green line denotes the point 4 and 2. And when you compute it, it's 2 times 4 for x1 plus 2, which is exactly equals to 10. And if we want to check all the points that satisfy this inequality, you might consider this point. Okay, we have x1 equals to 2 and x2 equals to 4. So if you looking at the point that I put my mouse on it, this value gives 2 times x1, 2 times 2 plus 4, which is 8. 8 is strictly less than equal to 10, so that is a legal point, a feasible point. And you could see that that point is, roughly speaking, on the left-hand side of this green line. Okay, so every point on the left-hand side of this green line would be a point that satisfies the first constraint inequality. Similarly, if we check all the legal points or feasible points for the second labor constraint, which is x1 plus 2 times x2 less than equals to 8, we could realize that all the bottom part below this black line would be a legal point. Okay. And notice that if we would like to making our good decisions, we have not only the single limitations or single restrictions. What we should do is we should make a best decision that satisfy all the constraints that we had. So the shaded blue part is the part that all the x1 and x2 pair that satisfy all the feasible constraint, all the constraints that we proposed. Okay, and in this sense, the target, geometrically speaking, is within this shaded region. We want to looking for a good point, such that this good point gives you the greatest value about 30 times x1 plus 20 times x2. Okay, and now you might see that we also have a dashed red line in this figure. It is a very interesting part, or one of the one of the best illustrations that I would like to show to my student in our OR courses is if you check the slope or you check the direction of this red dashed line, you might realize that it is nothing but 30 with respect to x1 plus 20 with respect to the x2. Okay, so the direction of this red dashed line, if you have taken the analytical geometry, is the orthogonal direction of this red dashed line. Okay, and what it means that, okay, for every point on this red dashed line, it gives you the same value of the objective. Here, the same value is 30 times x1 plus 20 times x2. Okay, so you can see that if you consider the x1 equals to 2, and in this red dashed line, you might see that, okay, luckily we have the x2 equals to 5. So that 2, 5 point is also on this red dashed line. And if we taking the 2, 5 point into the objective, which is 30 times 2 plus 20 times 5, which is 60 plus 100. So the value is 160, which is exactly the same if you taking the value for 2 to the objective, which is 30 times 4, 120, plus 20 times 2, 40. Okay. So as you can see that all the points on a single dashed line, they take the same value. But we notice that what we want is we're trying to looking for the best objective value. So every point in the shaded part will be a choice, will be a legal choice, a feasible choice. So we keeping the direction of this red line unchanged and trying to moving this red line within this shaded part. And luckily, you might realize that if we push this red line to the right-hand side as further as we could, you could see that, okay, the most furthest part is this 42 point. Okay, and that means, okay, we somehow pushing our objective value and get the maximization. So this is just an introductory idea on what it means. Maybe let's consider a quick first question and trying to remind you what we have discussed before. So let's say that suppose you are managing a company and now you meet the following statement. Uh, Someone says that, okay, we only have 10 units of resources. So is this an objective function or a constraint? Okay, you can type your answer in the Zoom chat and I will take a look. Yeah, very nice, very nice. That's a constraint. Because this is something, so the most easy way to differentiate from the objective to the constraint is, okay, whether it is the target or is it something that you would like to achieve. This is not. This is something like a constraint or limitations that tell you that, okay, now we only have these many type of the time or this many money and we could make our decision within this provided resources. Okay, let's move on to see some of the examples that will utilize the linear programming. As you can see from the right-hand side, this is an illustration of a data center utilize a lot of NVIDIA GPU. Okay, and now if you would like to train a large language model, and you could consider yourself as a CEO of a tech company. So you need to like allocating the computation resources to different tasks of a large language model. Okay. But somehow what you want to do is, okay, you want to making or you want to allocating the computation resources in an efficient way. The efficient means that somehow you want to minimizing the cost and the energy that you minimizing the cost and the energy because you know that okay for current very large for the very large language model with for example 18 billion of the parameters oh only training once we are taking you know, I think it's about like hundreds of million US dollars. Okay. So to do this good allocation on the computation resources and scheduling, managing the energy, handling the carbon dioxide emissions, all these tasks could be simplified into a linear programming problem. And you can see from the right-hand side, what we want is we set the little xij to be, okay, if you have a different type of the tasks, they all indices by under script little I, and also you have a set of the GPUs, and each of GPU are under subscribed by the little j. We utilize the decision variable xij to denote how many portion of computation tasks from the computation task I, sending it to the j's GPU. Okay, so easy to realize that this value should always be greater than equal to 0 because if we consider the whole task load as maybe the number of the flops that you need to devote it to in order to making this computation, to complete this computation, this xij denotes the number of flops. So they should be greater than equal to 0. And we notice that for the ICE computation task, it could send to every possible GPU card, but the summation of them should be equal to the task load. Okay. Similarly, if we are only focusing on one GPU card, the J's GPU card, the all task load that is allocated to this GPU should be low upper bounded by its capacity. So, for example, in a unit time, this GPU could only provide you, for example, like 1 billion of loops. Then, if you would like to ensure that it could complete the computation task on time, then the task load assigned to this GPU cards should be less than its capacity. Okay. And finally, we should minimizing the total energy or the total power or electricity. And we could notice that a simplified idea is that the energy that we devoted is proportion to the tasks upon upon the GPU it sent. Okay, so this is the simplified linear programming formulation. And if you would like to check for details, you might search for this large-scale cluster manager. And I think it becomes it has a blog and it gives you a very brief introduction on in detail what their formulation looks like. Second, if you want to check some micro-scale operations research, you might see in Singapore, you might realize that okay, we utilize this kind of robot that assign or deliver the hot food and pencils to deliver hot food and pencils in the HDB East. Okay. And still, as we could realize that we, as a manager, we would like to maximizing the deliveries or maximizing the efficiency. However, we should be ensure that this type of the robot has this efficient electricity power. So the constraint are respect to their battery limitations and also the charger availabilities. Okay. So here's the simplified formulation. So as you could realize that we utilize the little x on the script little f to denote the number of times as a delivery for the hot food. And we use the little x on the script little p to denote the number of times as a delivery for these pencils. Okay. And usually the food delivery is more urgent than the pencil delivery. And in this sense, okay, as you could realize that if we want to maximize the efficiency or maximize something that we could get paid, the coefficient corresponding to the hot food is a little bit greater than the coefficient with respect to the XP decision variable. Okay, so this is our objective. We still want to maximizing this objective. And we know that we are respecting to two constraints. One is about battery limitations and another is about charger availability. So we add this type of the constraint. And lastly, we would like to ensure that the number of times should be positive. And the one thing that I would like to point out is I add an integer in for the last type of the constraint. Because somehow, if you want to do it in a more realistic way, so somehow we should say that, okay, the number of times should be integer. It doesn't make sense if you say that, okay, now I deliver hot food for 1.5 times. That half time, that half time cannot be translating into a legal decisions under this setting. Okay. So the similar situation could also happen in many other places. And if you would like to get a detailed notification on what this under this setting, what the detailed things goes on, you might check or Google search for this title, Autonomous Delivery Robot Trial. Okay. Let's check have the second question. So in previous cases, we realized that for the HDB robot delivery, we have two types of the constraint. Now, suppose the situation changes a little bit, and we install 5 more charging ports to our robots. Let's say that for this constraint, the first decision variable plus the second decision variable less than equals to 10 charges. Now we have additional 5 more, so the constraint is upper bounded by 10, now improved by upper bounded by 15. So if we consider the linear programming mathematical feasible region, which I mean the shaded blue part in our previous slide. So geometrically speaking, does this shaded blue part shrinkage or expand? So you can type the either shrink or expand in the chat. Yeah, expand. That's great. That's great. Oh, I see. I find a question that asked by Luke Jim. Okay, as a network optimization problem. Oh yeah, that's an interesting question. So usually for the network optimization problem, you could consider like, okay, either you could setting the decision variables or place the decision variable on each of the node, or you could, if you want to uh, checking for example, the max flow and the min cut problem, you could send in the decision variables on each of the edges, like the type of like Xij, where the little I denotes the outcoming vertex and the J denotes the incoming vertex. Okay, okay, we can discuss that later. And okay, I also see another question asked by Joe Y. So okay, talking about so in the robot control problem, referring to frequency of deliveries. Uh, yes, this is easily speaking, you can consider it as the number of times that the number of time of delivery in a unit time range. But it is, of course, the frequency of the delivery. And if you taking the frequency, then in this sense, the little xf and the little xp could be fraction. This case, we do not the integer constraint in the last part. How many robots are assigned to? Okay. So the how many? So more briefly speaking, it's like the frequency and the number of the robots their multiplication would be your little x under script by f, and similarly as the little x under script by p. Okay. Yeah. So I think most of you get the idea that when we increasing the right-hand side, it would be expand. And so here's the mathematical explanation. When we check whether the feasible region is shrink or expand, the only thing that we need to do is, okay, we could see whether an original legal or original feasible point would be still origin in the new constraint. When it is true, then we could say that the feasible region expand, or at least not shrink. And when it is not true, then we could say that, okay, the feasible region is shrink, or at least not expand in this sense. Okay, let's move on. Now we could consider something in a little bit greater scale. We know that Singapore has a lot of industry about maritime, and they have good supply chain and logistic industry. So we know that, okay, if you at the port, then you might see that a lot of ships that they need to refueling every day. And if you are the center manager of this pod, that you need to scheduling you need to scheduling which fleet or which ship they need to refueling first, and which should be due after that. Okay, so we need to scheduling a limited fleet of bunker tanks and to service the arriving mega ships kind of stuff. Okay. And our target, unlike previous objective, that is usually maximizing the efficiency, maximizing the profit. In this case, we would like to minimizing the shape waiting times. Okay. So if you check the right-hand side part, you could realize the simplified formulation. For each of the little x under script by Vt is uh, the corresponding decision variable, which check whether the shape p, the shape v would be serviced at some point. Okay. So the objective, this capital A under script little v denotes the arriving time of that shape, and this little t denotes the corresponding time after they complete the refueling process. Okay, and their differences is the waiting time. So we would like to minimizing the waiting time for all shapes that get in. Okay. So the first constraint is about is to say that, okay, every shape we could only serve once. Okay. So this little t denotes the time point that after the arrival time, and we know that each of the simplified model only assumes that each shape fueling once. So the summation of them equals to 1. The second constraint denotes the corresponding value, because for each of the shape, their tanker capacity are different. So, and that the tanker capacity, are bounded by this value. So it could service at most to the left-hand side. If the left-hand side is strictly greater than the tank capacity, then okay, there's no resources, there's no filling oil. So okay, this tanker could be temporarily closed. Okay. And the last constraint, other than the previous cases, we show it greater than equal to zero. Here we just making them as a binary cases. Okay, so this is a simplified formulation. And if you would like to have a more realistic and a detailed idea on how it works, you may Google for this name. It's a just-in-time planning system. Okay. And I also showed MPA website of Singapore and see that how they did. Okay, let's move on. The next example is talking about the hospital staff puzzling problem. It's trying to like, okay, ensuring that every time, 24 hours a day and 4 days a week, we always have efficient doctors and nurses in the hospital. But the constraint is the following. Every doctor and the nurses, they are just a human, not a machine, so they have their own requirements. They could not conservatively working for very long time, or let's say more than 5 days in a week. And as the manager of a hospital, so you might consider looking for an automatic scheduling strategy that you try to minimizing the hiring cost. You do not want to hire in too many doctors and nurses. You do not have the enough space. And also you have some budget limits every year. And also you need to like maximize the well-being. Okay, so if you check the right-hand side figure, so every XJ denotes, okay, denotes the duty of some specific uh, uh, healthcare hospital staff, okay? And the objective is trying to minimizing the cost of shifts. Okay. And the capital CJ denotes the corresponding payment for different hospital staff. And here, the first constraint demand represent the demand on the day I is usually like, okay, from Monday to Friday, usually we need these many, say 100 many doctors. And on the weekends, maybe, okay, this hospital, they always meet the high peak in the weekend. So this DI might be greater than the weekdays, let's say from moving from the 100 to 150, something like that. Okay, but I should say that this type of the constraint are much simplified uh, in this case. I'll just show you as an example, and you could check this nurse rostering problem. Also, you could find the related references on the Wikipedia. Okay, let's move one more. So this is, I think, the last example I would like to share with you. Is okay if we somehow goes a little bit further. Then let's see how our operations research work with the generative AI. Okay, So usually if you utilize let's say the ChatGPT, DeepSeek, Qwen, let's say Gemini, okay, this type of the language model could help you to creating a good linear programming. And what they need is just a prompt that describe your problem in natural language. So, uh, mathematically speaking, how they generating the code? They generating the code or they written out a good linear programming model uh, based on some type of the sequential generated uh, procedures. And in in principle, or an easy way is if you're looking at the right-hand side, if you give the prompt is okay, I would like to minimizing, for example, this case, minimizing transport cost, or similarly, you could just copy and paste the first example that we showed in very early slide about that manufacturing cases, copy paste it into the language model. It also could help you to get or output a linear programming. But how it does? So if you split their output linear program into several components. Let's say we use this yi to denote the word minimization. We use this little y2 to denote the objective function. And we use the y3 to denote the word subject to. Then the math behind the language model generator, it could be formulated into this maximization problem. Well, if you have studied probability and statistic, so you might realize that this is corresponding to the likelihood. And every time what if we want to generate a new word, for example, if I would like to generate y3, so we need first to put the prompt as your very high level information, the task that you need to know, that the language model need to know. And also they need to go before and check what I generated in previous. The language model may realize that, okay, in previous, I just written out the whole objective function is a minimization. And after that, I written out the objective is some coefficient times the decision variable. Now, what I need to prepare to written out the constraint. But before I written out the constraint, I realize that I need to first written down this S point, T point as a shorthand notation to subject to. Okay. And this output could uh, maximize the likelihood or maximize the most meaningful result to the language model. So this is a brief underlying math explanation on how the language model generates these words. Okay, so if you are interested in that, Microsoft has a good survey paper on how this language model help you to do this generator tasks. Okay, so let's get to the last question. So let me know which of the following task is not a typical operations research problem. The first one is routing a public bus or designing the route of a public bus. And the second is designing a company logo. And the third one is scheduling some hospital nurses. For example, their working time and okay, how many staffs should be at a specific day. So you could drop A or B or C in the chat. Yeah, great, great, great. Designing a company logo. This is maybe relatively speaking, is a kind of art task. It's not a operations research task to do. Okay, let's make a conclusion of this Zoom lecture. So why I believe the operations research is interesting and important. So it's high demand. We could see from the previous examples, okay, we have a massive need for analytics and also to making good decisions. And we have these a lot of demands in different type of domain. For example, the tech company, for the finance company, for the consulting, for the government, for the healthcare, etc. and etc. Okay. Okay. And also, we might realize that, okay, if we meet some complicated tasks and also restricted by some difficult constraint, our daily heuristic or just experience might not give you always the best solutions. So we need mathematical models and some technical tools in operations research to help us to do these decisions. Okay. Lastly, we have measurable impact because we could always notice that our task is trying to maximize the profit, minimize the waiting time, minimizing the cost. So we could see that, okay, once we do the best decision, how much we could improve comparing with the heuristic or the experience decision. Okay. And that's what I would like to talk about today. This operations research is engineered to make a better tomorrow. And I'm willing to share some of the comments and ideas or insights about the operations research after that. So thank you very much for attending and thank you very much for your time. Any questions and comments are very welcome. I will stop share my slide for now. Okay, so if you have questions, you could just put it in chat box.